Hello there. My name is Jacob Yeager with the Creighton Energy Technology Program. I'm here to walk you through our standard operating procedure for carrying out an external quantum efficiency measurement on a silicon solar cell. The goal of this lab is to essentially find the ratio of charge carriers collected by the solar cell versus the number of incident photons on the cell. In simple terms, this means that we're taking the number of photons hitting our solar cell, assuming they get absorbed by the cell, and comparing that to the number of electrons that are leaving the cell.
We will be using our Oriole monochromator with a lens fixed in place to help focus our beam here, a silicon encapsulated panel, a Keithley power meter pictured here in the back, and it's hard to see, but we'll also be using a resistor wired between both of our leads of our solar panel. And the reason we're doing this is because our Keithley meter is actually not sensitive enough to be reading the low voltages or the low currents coming out of this encapsulated solar panel. So what we're doing is we're increasing the resistance, measuring the voltage, and then using V equals IR, we can solve for the current there by solving V over R. So in this experiment, we'll be measuring the resistance and the voltage being produced by the panel. We're going to have to use some optical mounting to kind of, not necessarily jerry-rig, but get our cell in place to where we want it. So I've taped off our lens over here so it's not moving anywhere, and it's in a fixed spot. That's an arbitrary distance. You can do that however you please, as long as the lens isn't moving between power meter and the measurement for the silicon cell itself. And what I've done here is I've gone ahead and created a little mask for the silicon cell that exposes the exact same surface area as the power meter. This way we know when we're measuring the flux on the power meter, we can assume that the same amount of photons incident on the surface are incident on our solar panel. So to get started, I'm going to hook this into the power meter. We've got the two leads, positive and negative. Doesn't matter really which goes into which lead. You'll end up with a negative reading or a positive reading in the Keithley, but it's fine either way. So I've got that hooked up, and then I'm going to come over to our optics mount here and go ahead and get it kind of in there as good as we can. And I'll take another gator grip just to keep this gator clip, excuse me, just to keep the cardboard pressed nice against our solar cell. So on the end of it, before I set it up to be to have light shining here, that's kind of what it looks like right there. Once you've got your solar cell set up, we can come over to the back of the monochromator and turn that on with the switch that's right here. Excuse me, the light source. And we turn the monochromator on right up here. It makes some nasty noises. Once we've got our solar panel into our optics mount, we're going to set it up so that the surface area exposed is being completely flooded with the beam of light, as we can see in the video. I'm also going to make sure that my solar panel is set at an arbitrary distance away from the light source, and we're going to match that arbitrary distance when we do the readings for our power meter. So for this measurement, I'm going to keep the power meter and the cell at 5 inches away from the light source. Okay, so to review what we've done in order to find the charge carriers leaving the cell, we've built a shade to get rid of some of the ambient lighting in the room, which we'll remove here. We've wired an encapsulated silicon solar cell into our Keithley power meters and mounted it 5 inches away from our light source and covered all the cell except for a surface area the same size as the power meter we'll use to find our power density. And we'll move into our Cornerstone utility program. And this is how we communicate with the light source and the monochromator. We will be scanning from a wavelength of 400 nanometers to about 1100 nanometers. And we use 2 filter wheels in this monochromator. So at a wavelength of about 570 nanometers, we need to switch over to the second filter. So we can scan again from 400 to about 560 by intervals of 20. But before we moved on to the rest of the wavelengths we want to research, we need to switch the filter from filter 1 to filter 2. For our second trial, we're going to get rid of the Keithley multimeter completely and the solar cell. And we'll replace the solar cell with our silicon power meter by Thor Labs, which is rated between 400 and 1100 nanometers. So using the power meter is a little lengthier process than using the multimeter with the solar cell. Every time we switch our 20 nanometer wavelengths with our monochromator, we have to manually change the calibrated wavelength that the power meter is reading. To do so, you'll select the bottom left corner that currently reads 680 nanometers on my screen. You hold down OK, and you hold down OK one more time. Now we're able to select from the 3 different digits and change them accordingly to what we need to. So we'll set this to, let's say, 550. Press OK, but then you have to press OK one more time to get back to the home menu, which looks like this. And now we have a set wavelength at 550, and the power meter is working. As it's exposed to light, higher readings, so we shade it, a low reading. So for this trial, we're recording only the power that is being read out by our power meter, which will allow us to find the incident number of photons per wavelength on the surface of our power meter, which will be the same number of incident photons on this surface, because the surface areas are the same and they are going to be set at equal distances from the light source. So we can get rid of our solar panel and we bring in our optical power meter. What do you know? We're about exactly 5 inches off of the light source, slightly ahead of it. So now that we're 5 inches away, we'll know that the number of photons incident on this surface will be the same number of photons incident on our solar panel. So now we put our cover back over our experiment like that, and we begin our trials for power. So once we've completed both trials, we're going to need to format an Excel document in order to keep track of all the data. I suggest you create this document before you run your trials so you can easily record the data as you go. In the first column, we have our wavelengths in the 20 nanometer intervals from 0.4 micrometers to 0.8 micrometers. If you want to cover a wider range and get more out of your experiment, you can cover the entire range of the optical meter, which goes from 0.4 to 1 micrometers. In the second column, I have the voltage read out in millivolts that I got from our Keithley multimeter. I converted those values to volts by simply dividing by 1,000,
And then I have a third or a fourth column dedicated to current. And like I said before, we didn't measure current coming out of our panel. We simply measured the voltage and divided by the measure of resistance, which we got here to be 387 ohms. So in order to find our current, we just divide the voltage values per wavelength by the resistance. In order to find the number of electrons per wavelength, then, we simply divide by the elementary charge, as shown here. In our second sheet, this is the information of the data we've gathered from doing the optical power meter trial. You'll notice the first column is dedicated to the wavelengths in micrometers again. This time the second column is dedicated to the energy and electron volts of that photon. And I got that from PV Education. You should know how to do that. That's just the power of a photon. I converted that to joules. If you want to know that conversion, it's right here. And then to find the power, I simply used our power meter, which read out in micrometers. I converted those microwatts. I converted those into watts. And in order to find the number of photons on that surface, I'm going to simply take the power that we've got in watts divided by the energy of each photon or each wavelength. And the reason this has an area here, the reason we can neglect that, is simply because the surface area that we illuminated is the same as the surface area of our power meter, or the illuminated surfaces are exactly the same. So again, we'll divide the power, which is here in watts, by our energy, leaving us with photon flux. Moving on from there, you simply record those values you get in this column, which is the number of photons, again, incident on the surface. And then we will move into our third sheet, which spits out our efficiencies. And what we do here is we simply divide the number of electrons coming out by the number of photons coming in and multiply by 100. And this should give us your efficiency. You can graph those results. And if you did it correctly, you should come up with something that kind of looks like this black curve here, which is our external quantum efficiency curve. And it should be pretty consistent, as you can see, through most visible light. It drops off in the end because of low energies and absorption lengths, and this drop is also dedicated to, as you can see, we're in the green, which is absorbed mainly in the middle section of our, in the middle or bulk section of our panels. So there's a lot of recombination going on compared to, again, blue, which happens in the front portion of our, or the front surface of our solar cell. And then after that, if you want to get an average efficiency, you just take all these values you got here and average them out. And that is how you do a quantum efficiency measurement.